This is the last of the series of lectures on the endocrine system. We're just going to finish up with organs that produce hormones that are not necessarily incidental hormones, but that's not the main function of that organ. So we consider them sort of secondary functions. Their primary function is something else. And I added liver to this list. It's often left off of lists, even though the liver definitely does secrete some hormones. The liver is usually associated with the digestive system, but it has so many other functions that it's really hard to pinpoint it to a single system. However, since its functions with digestion and nutrition are certainly primary on its list, that's where we'll study the structure of the liver and kind of finish up the liver. For now, we'll just learn a few of the endocrine functions, most of which are going to be involved in metabolism, so we'll look at the details as they come up throughout the rest of the semester. The intestines, definitely digestive hormones, so we'll worry about those when we get to the digestive system. The kidneys are technically part of the urinary system, but they have hormones that have functions for other systems, so we need to look at those now. The heart, again, functions mainly for cardiovascular systems, so we'll look at them very briefly and worry more about the details later. The thymus we'll study with the immune system, and the gonads definitely we'll wait till we get to the reproductive system for the details. For now, we're just kind of hitting some highlights, so you just need to associate these organs as having a primary role in some other system and a secondary role as endocrine organs. The liver does produce some hormones that we classify as somatomedins. We usually associate these with growth hormone. They do have some negative feedback effect to control growth hormone. That effect is called a somatostatin effect because growth hormone is also called somatotropin because it stimulates the soma, the body. We're not going to worry about the roles of the somatomedins. Of course, as we do more research and learn more things, that list just gets longer and longer. So just associate somatomedins with the liver, even though other tissues secrete them. As we'll study when we get to blood pressure, there's a hormone called angiotensin secreted by the liver in an inactive form. It has to be activated by an enzyme from the kidney, which we'll visit in just a minute. EPO, also secreted by the kidneys, but some is secreted by the liver. And EPO stands for erythropoietin. It stimulates the maturation of red blood cells, and thrombopoietin stimulates the development of platelets. There's a hormone that regulates iron levels in the body. There's a hormone that regulates the pancreatic beta cells. That's just sort of the current list of what we know is being secreted by the liver. The intestine produces hormones for digestive function. We're not even going to learn the names of them for now. We'll save them till we get to the digestive system because that's predominantly what their role is. The kidneys produce two hormones, EPO, which we just mentioned with the liver, but also a hormone called calcitriol, which we've already looked at. It helps regulate the absorption of calcium and elevates blood calcium levels. And the kidneys also secrete an enzyme called renin. Some people pronounce it renin, but we'll see there's another enzyme called renin. And it comes from the kidneys, which the term is renal. So let's call this one renin. And again, we'll worry about it more when we get to regulation of blood pressure. So here is a diagram out of your textbook on the production of calcitriol. It's kind of complicated. And as you can see from the top of the picture, sunlight absorbed into the skin causes the epidermal cells to take some cholesterol, which is just naturally found in the body, and it catalyzes, the sunlight catalyzes the activation of one step in the production of vitamin D, and the energy from the sunlight stimulates the conversion of cholesterol to an intermediate molecule called cholecalciferol. You do not need to know the intermediate names, but this is what we refer to commonly as vitamin D. So you can also get vitamin D from the diet, and that's your two sources. Generally speaking, you can only get about 20% of what you need from the skin, and it does require sun exposure. So we need about 80% of it from our diet. Dietary sources for us include cold water fish like salmon, and typically we get vitamin D as an additive to dairy products. So what happens to the cholecalciferol? Well, it circulates through the blood, and when it gets to the liver produces a second step in this conversion. So it's still not a functional hormone at this point, but from the liver it's going to go to the kidneys, and the kidney cells are going to finish the formation into the final hormone calcitriol. And calcitriol is a steroid hormone from the kidneys, therefore it promotes protein synthesis, and apparently its target cells are actually producing more protein transporters, which allows them to absorb calcium from the diet, absorb calcium actually in the kidneys, reabsorb it from the urine, and possibly from the bones as well. It does require PTH. PTH, remember, stimulates an increase in calcium in the blood. PTH is required by the kidneys to make the calcitriol, but it's also required to turn on the effect of calcitriol in its target tissues. Now, that's probably way too much information. So the bottom line is you get vitamin D from your diet and from production in your skin, and that vitamin D is processed by the liver, and then in the kidneys, PTH stimulates the formation of the active form calcitriol, which again combined with PTH increases calcium absorption. So here we see a flow diagram showing us how renin and angiotensin work. And what you need to remember here is that angiotensin is actually produced by the liver, and it's just sort of dumped by the liver cells into the bloodstream all the time. So you always have a certain amount of angiotensinogen in the circulation. The OGEN at the end tells you it's an inactive precursor. So when blood pressure drops too low, the kidneys sense the drop in blood flow and secrete renin. And renin stimulates the activation of angiotensinogen to angiotensin, and angiotensin does a number of things, one of which is to increase blood pressure. Now, we're not worried at this point about the steps in this process. We'll study these when we get to blood pressure regulation. So for now, you need to remember angiotensinogen from the liver, renin from the kidney to activate it. That raises your blood pressure. The other thing we see happening with the kidney at this point is that when the oxygen level is too low, that's a condition called hypoxia. That stimulates the release of erythropoietin, that's EPO, and that stimulates the bone marrow to increase the production of red blood cells, and that raises your oxygen level back up. So again, we'll look at this in more detail when we study the blood. So for now, what you need to remember is there are two things that come from the kidney, EPO and renin, that regulate aspects of the blood, and one thing from the liver, angiotensinogen, that also helps regulate the blood. So still looking at cardiovascular effects, the heart itself secretes two hormones. These hormones are called the natriuretic peptides. Natrium means sodium, and uretic refers to urine. So these two hormones, ANP and BNP, are going to be secreted when you have chronic high blood volume, and that stretches the heart, and it's that chronic stretch of the heart that stimulates predominantly the right atrium to release these hormones. And what they do is they stimulate the kidneys to get rid of more sodium and therefore water, and that helps bring the blood volume down. So again, what we're looking at is a cardiovascular regulating hormone, just as EPO was and renin-angiotensin were. So we'll worry about the details of these later. For now, you need to remember that the heart is secreting these hormones, ANP and BNP, which stimulate the removal of sodium and water from the body and reduce the blood volume. The thymus is considered a lymphatic tissue, a tissue of the lymphatic system, and in addition to producing new T lymphocytes, it also produces a hormone to regulate those T lymphocytes. So we'll learn the details of this when we get to the immune system. The gonads produce the sex hormones. Again, these are steroid hormones. Testes in the male, ovaries in the female. The primary androgen, that is a male generating hormone, is testosterone. Again, stero in the name tells you it's a steroid hormone. In the ovaries, there are two groups, estrogens and progestins. The principal estrogen is estradiol. The principal progestin is progesterone. Again, you see stero in the name, reminding you it's a steroid hormone. And we'll worry about the reproductive effects of these hormones way at the end of the term. This isn't really an organ, it's a tissue because adipose is scattered throughout the body, but adipose cells do secrete a hormone called leptin. Leptin is necessary for feedback control of appetite. It does feed back into GnRH regulation, which we're not really worried about at this point, but we'll worry more about leptin when we study metabolic effects. Okay, so that's the quick run through of all of the secondary endocrine organs, and now we're going to focus on some of the coordinated effects of the endocrine system. An antagonist has an opposite effect. A synergistic effect occurs when the effect of two hormones together is greater than the effect of either one of them by itself. A permissive effect is when you need one hormone for the other one to do anything. And integrative effects, of course, is when they all kind of add in together. So we're going to look at the integrative effects of hormones for growth. You have, of course, growth hormone. You have the thyroid hormones, insulin, PTH and calcitriol for calcium addition to bone. And, of course, the reproductive hormones have anabolic effects. So growth hormone is absolutely essential for muscular and skeletal development in children. And we know this because if a child has a deficiency of growth hormone, then their growth is diminished, and we classify them as pituitary dwarfs. In adults, growth hormone helps to maintain normal metabolism, and that includes sugar levels and lipid reserves. In excess in adults, there is an overstimulation of bone growth, resulting in a condition called acromegaly. The thyroid hormone's absolutely crucial for normal metabolism, and without that, children fail to grow, the nervous system will not develop, they're profoundly mentally retarded and short-statured. This is very treatable. We can give thyroid hormone as a supplement, so we don't usually see this kind of hypothyroidism go untreated in children. For the purposes of growth, insulin helps cells not only take in glucose, but also the amino acids, and this is necessary, of course, for protein synthesis. PTH and calcitriol are required to keep the blood calcium level high enough to get the calcium into the bones, so that's certainly an aspect of growth. And the reproductive hormones in both males and females stimulates protein synthesis in target cells. And that's going to be in muscle mass and in bone. And then, of course, at puberty, when these are secreted, then it leads to sex-related differences, such as the widening of shoulders in a boy and the broadening of the hips in a girl.